Good morning. Right, I hope you had a good weekend. Let us begin. So this slide starts with very dangerous words. The derivation of this is off syllable, which may be a cue for you to leave the room or fall asleep, but that would be wrong because firstly I think you'll find it's rather interesting, and secondly it doesn't last too long and then we're firmly back on piste again. So what I'm going to do is to derive the orbiter equation, and then we shall see that a solution to this is our elliptical orbits. So we start with our general expression, which should look very familiar now, for acceleration in polar coordinates, and we deal with a central force. And we're particularly talking about gravity. So this tells us that the radial component is minus alpha over r squared. Alpha is just my shorthand for big G, big M, little m. Save me writing all of that. And then that the azimuthal component is 0. Okay. Right, now as we've already seen, the azimuthal component being 0, that leads to the consequence that angular momentum is conserved. Right, so we've seen this, we don't need to rehash it. So that is that m r squared theta dot is constant. And that can be rearranged to give us an expression for theta dot, which is j over m r squared, which is an equivalence we're going to be making use of. Okay, so let's focus in on the radial component, however. So we have that m r double dot minus r theta dot squared equals minus alpha over r squared. Now I'm going to divide through by m. I'm going to leave the r double dot on the left hand side, move this to the right hand side and make use of this expression here. Okay, so I left with r double dot on the left hand side, then minus alpha over m r squared, and then I move this to the other side and use this expression for theta dot, and I get plus j squared over m squared r cubed. Right. Now I'm going to make a substitution. I'm going to define u as being 1 over r, because this is going to eventually enable us to write the final expression in a compact form. And so the right-hand side becomes, r double dot, which I won't touch yet, I just concentrate on the right-hand side. We get, put that term first actually, therefore we're going to get u cubed j squared over m squared minus u squared alpha over m. Okay, so having an equation where the right hand side is in terms of u and the left hand side is in terms of r is not very useful, so we now need to rewrite the left hand side in terms of u. Let's see if we can do that. Well, let's start by noting that r dot, so this is r double dot, but r dot can be written as d theta by dt, dr by d theta. Okay, so this will soon become apparent. Now d theta by dt, that's nothing more than theta dot, and so that is j over m r squared dr by d theta. Okay. Now, if we look at that and squint for a minute, where we say, aha, what about if I write this as d of 1 over r d theta? Let me write the whole thing. Right, so this is a cunning manipulation, and that is just to spell it out in obvious terms. D over 1 over r d theta is the same as minus 1 over r squared dr d theta, right? So by writing it in that way, I've managed to get rid of that r squared, and 1 over r, that's nothing more than our u, this variable we've defined. So that is minus j over m du d theta. So that was an unexpected and serendipitous discovery. But that's just r dot. We need r double dot. So r double dot is the derivative of this. So again, we can write this as d theta by dt. And then d by d theta of what's everything there. Once more, d theta by dt, that's nothing more than theta dot. This is a constant. Now, this differentiating that by d theta is trivial. We just end up with minus j squared over m squared u squared dtu by d theta squared. Okay, so the d by d theta in that clearly gives this. The substitution is as before, but instead of having 1 over r squared, we're writing it as u squared. Okay, and so now we have an expression for r double dot expressed just in terms of u. So we have therefore minus j squared over m squared u squared dtu by d theta squared, and then that is equal to the right-hand side. Where's it gone? Yeah, on the second from top board. Just write that down again. So that's u cubed j squared over m squared minus u squared alpha over m. So if we tidy this up, it then becomes the rather elegant expression multiplying dtu by d theta squared equals minus u plus, now I'm going to make another substitution, 1 over r0, where r0 equals j squared over m alpha. Okay. Okay, so that was worth it, making that substitution for u. So now our expression for our Newton's second law has been re-expressed in this rather compact form. So can we solve this? Well, certainly, but this is not a maths lecture, so what I've done here is actually told you the solution. But let's just justify that this works. So c is a constant and theta naught is a constant. So let's just put that in and see it does the job. So u equals 1 over r0 plus c cosine theta minus theta naught. So in this equation, I need a double derivative of this with respect to theta. So du by d theta is just going to give me minus c sine theta minus theta naught, and dt u by d theta squared is just going to give me minus sine cosine of theta minus theta naught. Okay. And so if I, and that is clearly the same as minus u plus 1 over r0, which as it should be. So it is a solution. Right, okay, we have this solution. Let's try and interpret what it means. So firstly, we can reorder and just put it in terms of let's put r on top, so we get r theta is equal to r0 over 1 plus CR0 cosine theta minus theta naught. Okay, and let us write, this is C, let's redefine something as E, little e equals CR0. So that's because that's a constant times something we've defined, so let's just redefine this as a new constant. I call it little e with a purpose, and we'll see that in a second. So we get r theta equals r0 over 1 plus e cosine theta minus theta naught. And this is the equation of an ellipse, not just of an ellipse, and other conic sections. So just to be clear, that is an expression which actually also defines a hyperbola, parabola, a circle. How can it define a circle, you might ask? Well, this parameter e here, e is the eccentricity. So this is, for instance, 0 for a circle. Okay. So if that value turns out to be 0, then the radius as a function of theta is a constant. So that is clearly a circle. But for an ellipse, the value of E will be between 0 and 1. Turns out that if E equals 1, that is a parabola. And if it is greater than 1, that is a hyperbola. But it's this case which will be absorbing our interest for the rest of this lecture. Okay. So this, therefore, let's regard this as the equation for an ellipse. It's got so it's got two constants. Well, it has two parameters driving it. It has or three. It has r0, has e the eccentricity, and it has theta 0, which is associated with a tilt. And this we can easily get away with. We can actually define our axes such that theta 0 is 0, and then the thing is not tilted. So, and this is what we'll do from now on. So what we'll do, we'll choose our major axis. So an ellipse has two axes. The major one is the longer one. This is the minor one. We choose our major axis to be as x, and this will imply theta 0 equals 0, i.e. no tilt. And then r of theta will be equal to r0 over 1 plus e cosine theta. And this will be the form of the expression which we will be dealing with from now on. Okay. So you might say, well, okay, you tell me this is the form of equation for an ellipse, but I thought I've seen an expression before, and there's various expressions, but just to write down the one you've seen before, which is the Cartesian one, that is x over a squared plus y over b squared equals 1. And these two are equivalent. We won't demonstrate this now, but you take my word for it, or even better, prove that to yourself. Okay, so the ellipse is a wonderful thing, and it has various parameters associated with it. So just note the parameters. Let's just see what we have. We have A, B, R0, and E. Okay, so A is half the major is half the major axis. B is half the minor axis. E, we said, is the eccentricity, and R0 is something which you can't conveniently draw in this picture, but it occurs in this expression. Now, there's obviously associations between these parameters. They are linked, and what we will do now is just spend a few minutes doing some fairly tedious algebra just to derive some of these relationships. Okay, you see a few of them scattered here. We will derive them, but these are just relationships between those parameters. And these will be useful because after this slide we'll do some physics again, and we'll make use of this. Okay? So bear with me. Okay, so firstly, let's just say, well, an ellipse, it clearly has a closest point and a furthest. There's a closest point to the focus. So what we should regard this as, let's be clear, let's interpret what's going on here. So the ellipse has two foci, focus 1 and focus 2, and this is the solution we have corresponds to a radial force which is situated at one of these foci. So we can imagine the sun is here and the planet is revolving around. So what we have demonstrated is that a solution of the inverse square law is that the motion will be an ellipse with the attractor, the sun, at one foci. Okay, and that, as you probably know, is one of Kepler's laws. Now, as it's going around this orbit, it clearly has a point when it's closest to this focus and a point when it's furthest away. This we call the perigee, and this we call the apogee. Okay, so the closest approach which is the perigee, that is when theta is equal to 0, that's clear. And then from the form of this equation, then you just get r min, for the minimum radius, is just r0 over 1 plus e. And then the furthest approach, which is the apogee, as theta equals 180 degrees, and then that's r max is r0 over 1 minus e. Okay. Now let's add those together. We have r max plus r min. So if you add the right-hand sides of these two things, you end up with 2r0 over 1 minus E all squared, okay? I skipped one intermediate line, but that is trivial. R max plus R min, let's look at our diagram. That is nothing more than the major axis. And that is the major axis, which is 2a. Okay. And so we get the first of our results, which is that R0 is equal to A1 minus E squared. So that's a relationship between R0, A, and the eccentricity. Having got that, and since we have these definitions for R min and R max here, we can immediately plug these in to get R max and R min in terms of these quantities. So let me try and write this in a compact form. R max, R min is equal to A1 plus or minus the eccentricity. Okay. So these are actually the relations which happen to be on the bottom of the slide, but it's best to note them here. All right, well, let's now try and bring B to the party. Get an expression involving B, which is the semi-minor axis. There it is. So firstly, let's consider this, let's look at relations here, in particular involving this triangle. So firstly, this introducing yet another parameter, but we'll soon get rid of it. The distance from the center of the ellipse to the focus, let's call that xc, and that plus r min is a. Okay. So xc plus r min equals a. Now we have this nice expression for r min, so we can immediately make use of that. So I can write xc equals a minus r min, which is minus a1 minus epsilon, which is equal to a e. Okay. So that's another expression, or I just rearrange that. I can write the eccentricity is xc over a. So, sorry, that is an expression involving yet another parameter, xc. But yeah, what I want to do, as I said, is bring B to the party. So let us study this. Let's construct a triangle here involving xc, r when it's here, and b. So this is a Pythagoras. And we can also make use of this definition of, well, this is how theta is defined. And we can also use a trigonometrical identity. So let me write these down. So at point A, we have r squared equals xc squared plus b squared. And we have cosine theta equals minus xc over r. Okay. So this is just trigonometry with this triangle, but be aware that theta is defined as the outside angle of this triangle. So if you squint a bit and do some trivial school-level trigonometry, you'll convince yourself that this relation is true with the requirement of the minus sign. Okay. So let's put this into the ellipse equation, because the ellipse equation involves cosine theta. So that gives me r equals r0 over 1, and there we have a plus e cosine theta. So this so I get minus e xc over r. So if I multiply through, this then tells me that R equals R0 plus E XC. Okay. Right, so now let's call this 1. So let's put that into 1. I promise there's not much more of this, we're almost at an end. So we get R0 plus E XC squared equals XC squared plus B squared. Before multiplying this out, I'm going to actually substitute in for R0. So we're going to sub for R0. And so we get A1 minus epsilon, sorry, A1 minus E squared plus, not only for x0, we can also substitute for xc. We have this expression for xc. So I'm going to try and eliminate this and get to something which just relates A, B, and E. So what do we got? So we have, this gives me E squared, A squared, and then the right-hand side will be E squared, A squared, plus B squared. Right, so this nonsense is almost at an end. We now have to, there's a squared here. Just a minute. There's a last A, yes, this is right. Who told me that? Now, this is really bad. As I was coming across here, I do have Mars bars, but they are in my drawer, and there wasn't time to go back. So come along tomorrow at 9 o'clock, and you will get your reward. So I was thinking, oh God, I've got to try and not make a mistake, but I knew I had all this mess in front of me. So I apologise, but you will be rewarded tomorrow. Right, let me try and keep a cool head. So with this, then, this clearly simplifies. I just get, yeah, we're in good shape now. So this is just A squared equals E squared, A squared, plus B squared. And so B is equal to A square root of 1 minus E squared. So that flailing about has given us a relationship between B and A. And finally, though it's not written here, for good measure, let me note that since R0 is equal to A1 minus E squared, then I can get a relationship between A, B, and R0, and here it is. So R0 equals B squared over A. So, I mean, this is not exhaustive. There are other relationships you could derive, but I think we'll agree that's quite enough. So let's now try and make use of some of these, coming back to the application of physics. Right, and clearly we're in the realm of Kepler's laws. Let's just recall what these are. So Kepler's first law is the orbit of every planet is an ellipse with the sun at one of the foci. So this we have shown just now by demonstrating that a solution of the inverse square law is indeed an ellipse with the attractor, the sun, at one of the foci. Kepler 2, a line joining a planet and the sun sweeps out equal areas during equal intervals of time. This we have already also shown last week or the week before. The final expression is Kepler 3. The squares of the orbital periods of the planets are directly proportional to the cubes of the semi-major axis of the orbits. And this we will show now. Just though with a minor diversion, this may look like something out of Victorian times to you, but not so long ago, the Treasury actually had a £1 note, if you can imagine such a thing. And that was the last time, and this gentleman looks familiar. This is Isaac Newton, and this is Newton contemplating planetary motion and the laws of universal gravitation. And so you clearly see ellipses here, and you clearly see the sun, but you note that the sun has been placed right in the centre of the ellipse rather than at a focus of the ellipse. So this is physically wrong, and this note has now been withdrawn from circulation, but I think that's more to do with inflation rather than physics. Okay, so Kepler's third law. It's a bit of a mouthful, but I'll let you read it again. So this is something which for a circle is rather trivial and something which you have demonstrated before. Let's just remind ourselves how it goes. So for a circle, we have mv squared over r equals big G, big M, little m over r squared, which I can write the left-hand side as m r 0 omega squared equals m r equals that. So R0, which is in our equation for the ellipse, as I showed you earlier, in the case where E equals 1, that is just the radius of the circle, hence this. So if I write this in terms of the period of oscillation, this is 2 pi over t all squared equals this. And so, just checking. So let me write all of this out again. This is R0 squared on the bottom. So multiplying through, we get R cubed equals T squared over GM over 4 pi squared. So this is correctly demonstrated, because for a circle is a special case of the ellipse, and the radius of the circle in that case corresponds to the semi-major axis of that ellipse. So that's something you've been able to do for a long time. But let us, I think you'll agree that it's far from obvious that the same relation should hold for an ellipse in general. So let us show that that is the case. Okay. Right, this is, okay, it's all written out here, but let me talk you through it. So I will write it again here. So we start with R equals R0 over 1 plus E cosine theta. And the equation I want to, of all these relations that we derived, actually rather than the two written there, but they trivially lead to this, we just made use of this. The final one we derived was that, and let me immediately make use of that. But R equals B squared over A 1 plus E cosine theta. And then, it might not seem obvious why this is the way to go initially, but believe me it is. Let us write it in the inverse. So we have 1 over R equals A 1 plus E cosine theta over B squared. Okay. So let me call this equation 1. we had an equation 1 a while back, but let me stay consistent with my slide else we'll get into a complete mess. It seems to be called 2 on the slide. Okay. And let me also make a trivial rearrangement and write an expression for a over b squared, which is 1 over r minus a e cosine theta over b squared. I seem to be called this 3. Now that looks a strange thing to do, but believe me, that's also going to turn out to be useful. Right, focusing on equation 2, 1 over r, let's start differentiating this, because what I have in mind is Newton's second law. So with Newton 2 in mind, okay, so we have something which we know is a solution to the equation, but it's written in terms of all the stuff we're interested in, such as the semi-major axis. So let's try and get this into a form which we can stick into Newton 2. And that's going to require that we have r double dot, right? So let us differentiate 2 with respect to time, and we get, therefore, r dot over r squared. Okay, we get a minus sign, I know, but we're going to get a minus sign on the right-hand side, so I'm going to cancel that as we go along. So this is a constant, we just need to differentiate that. We get minus ae sine theta theta dot over beta squared. And cancelling the minus signs, we get ae sine theta over b squared theta dot. And so we can write this as r dot multiplying through by r squared. We get a e sine theta over m b squared j, because of course I've made use of, you knew I was going to do this, but j is equal to m r squared theta dot. Okay. Well, we're after r double dot, so let's do that all again. But this is going to be easy now, so I'm just going to get ae cosine theta theta dot, and I'm going to substitute for theta dot again. Well, let's write out. So it's ae cosine theta j theta dot over mb squared. So again, substituting for theta dot, I get ae cosine theta j squared over m squared b squared r squared. Okay, so we've got something which we can now think about putting back into Newton 2. So we have, for radial acceleration, that AR equals R double dot, but that isn't all. We have the minus R theta dot squared. Okay, so R double dot, we now have something for that. That's great. Let's stick it in. So that is AE cosine theta j squared over m squared b squared r squared. And this, the second term involving theta dot, well, what do we do? Well, of course, we write it in terms of j squared. So that is minus j squared over m squared r to the cube, I think you'll agree, which is taking the j squared over m squared r squared out, squared r squared. That is a e cosine theta over b squared minus 1 over r. At this point, you look at that and you say, this looks familiar, and it is true because, as I said previously, the expression's gone, let me put it up on the slide. We said that this will be useful, a over b squared over b squared equals this, right? So the right-hand side of this is nothing more than what we have here with a minus sign. So excellent. So we have, therefore, that AR is equal to minus j squared, we've got an A over m squared b squared r squared. So this is such a nice relation, it's worth pausing at and just contemplating. So why is that nice? Well, it's clearly, it tells us that the acceleration has this inverse r squared dependence, okay? So we see that the solution of elliptical motion has led to an inverse square law, which should not be surprising because it's all a cheat, because the solution of elliptical motion we actually got at the start of the lecture from solving the inverse square law equation. But it's still good to see as we work through this that we have recovered that relation. So we're in good shape. Okay, so now we can use Newton's second law because we have the expression for the acceleration. So we have that minus m of, so we have, yeah, so the acceleration, so the ma term gives us minus m j squared a over m squared b squared r squared, and that is equal to the force, which is minus big G, big M, little m over r squared. So there's m's on either side, there's r squareds on either side. So this is already looking quite exciting because the r squareds are going to go, and we get left with big G, big M equals j squared a over m squared b squared. Okay, so this is a very promising and interesting looking expression, but it doesn't yet look like Kepler 3. So let us try and think what we can make use of. Well, we know what we don't have here yet is anything involving the time period of the motion. We've got a dependence on A, which is good. We want that. There's B in there, which we probably want to get rid of, but we don't have the time period. So Kepler 2, what does that tell us? So that tells us that that's equal periods are swept out in equal times. So we can, that is that dA by dt equals a constant, and that constant actually is equal to big J over 2m. And this is something we saw in lecture 16. So that is a result. Okay. So this, therefore, the time period big T, that must be related to the area of the ellipse divided by dA by dt. Okay, that must be true. So that is the period, and this is the area of the ellipse. What is the area of an ellipse? So that is, again, you can pull that out of a geometry book. That is nothing more than pi times a times b, okay? Not something I will prove, but it looks plausible. In the case you have a circle, a and b are the same, and it's just pi r squared. Right, so this tells us that j is equal to 2 pi a b m over big T. Okay, so this we now can put back into what I labelled here as equation 6, and we get T squared equals 4 pi squared over big G, big M, a to the cube. And this is Kepler's third law proven for an ellipse. So is this, so any piece of theory in physics is absolutely worthless unless it's corroborated by experiment. Is this corroborated by experiment? Yes, it is. So this is well, this is just the log of the log, but if you plot the log of one against the other, you expect a linear dependence, and you do. And if you measure this gradient, it's entirely consistent with what Kepler had shown. Just historically, of course, we know what happened. I mean, Kepler got this relationship just by looking at the data and observing that this relation existed. He had no idea where the relation came from. That was shown by Newton. Right. I'll just finally, what I want to show is that this result of elliptical orbits, we could actually get at this from a completely different way, which is looking at the energy of the orbit. So we have that. So now writing expressions we were playing with last week for the energy, we have E equals a half m r dot squared plus j squared over 2m r squared minus alpha over r. Okay. Now we're interested in the minimum radius and the maximum radius. So at r min and r max, how are they characterized? Well, one thing which defines them is that r dot equals 0. Okay. So then we have E equals j squared over 2m r squared minus alpha over r, which now if we try and solve in terms of r squared, we multiply through and we get r squared plus alpha over E r minus j squared over 2m E equals 0. And this is a quadratic which we can solve, so we get r, and this is going to give us max and min. Okay, so let me just, you know how to solve a quadratic equation, so let me just write what one gets in the most concise form. You'll find you get in front a minus alpha over 2e, and then a 1 plus or minus 1 plus 2ej squared over m alpha squared to the half. Okay, so I apologize for missing out the few intermediate steps, but time's coming along, and you know how to solve the quadratic equation. So you look at this for a bit, and then you say, well, earlier on we were looking at equations for ellipses. Let's go back to them. Yeah, you see at the bottom there, we had that r max min is equal to a 1 plus or minus e. So this looks very much of the same form. So this has the same form if we associate. So A would then have to be equal to minus alpha over 2e. You might say, I don't like that because A represents a geometrical quantity and that's clearly positive. But then I would say, aha, but for a bound orbit, the energy has to be zero. This is something we concluded when we were looking at these effective potentials. So recall E is less than zero for a bound orbit. So this means that A is positive, so that's great. And what else would we conclude by looking at that? We'd conclude that E is equal to 1 plus 2EJ squared over M alpha squared to the half. Okay. Okay, so that is not a very simple expression, but what we see is that there is a relationship. I mean, we've got something of the same form, so from our knowledge of what elliptical geometries look like, and from the energy equation, we have concluded that the orbits must be elliptical, and we have made an association between the energy of the orbit and its geometrical properties. Okay, so just looking at this last relationship here, if I square this out, I can just rearrange this. I get then that E is equal to M alpha squared over 2J squared E squared minus 1, which is the same as alpha over 2R0 E squared minus 1. You know, probably on the second slide of the lecture we actually defined R0, and we said that R0 was equal to J squared over M alpha. Okay. So again, we find that there are these very nice relationships between the geometry of the ellipse, the R0, and also the eccentricity and the energy and the angular momentum. Okay, so we have one more slide to go, but I think I will re-summarize this tomorrow and show that slide, and then we'll move on. So see you tomorrow. Good morning.